Welcome to the lecture series on analog communications, module 5. Currently, we are talking about estimating the figure of merit for continuous wave modulation schemes. By this time, you might have understood a figure of merit is a performance evaluation metric to know which continuous wave modulation scheme is better. Among different continuous wave modulation schemes, that is a double sideband full carrier AM, double sideband suppressor carrier AM, single sideband suppressor carrier AM, frequency modulation. Till now, we have derived figure of merit for DSB SC AM, that is double sideband suppressor carrier AM. We have proved that the figure of merit for DSB SC is unity. Now we continue our discussion with the estimation of a figure of merit for double sideband full carrier AM. This is typically sometimes called as AM receivers with envelope detection. Why? Because in DSB FC AM, we use envelope detection for recovering the original message signal. So let us continue our discussion. And what is the fundamental step in our discussion? As usual, draw the receiver model. So which receiver we have to draw? We have to draw the double sideband full carrier AM model. And what is the commonality? The commonality in all the receiver models is the input is fed with a modulated signal which is corrected by a white noise W of t, followed by an equivalent IF filter or IF section. The characteristic of this IF filter or IF section are very narrow. This IF filter converts a wideband signal into a narrowband signal, already known. And the difference between different receiver models from one another is a demodulator. Now, in the current discussion, as we are talking about DSB-FC, double sideband full carrier AM, the ultimate demodulation scheme used is envelope detector. So, as usual, output of the IF filter is X of t, output of the envelope detector is Y of t, which is going to be consisting of both a message component as well as the noise component. So before going into estimation of the output or demodulated signal, let's concentrate some time on the input side. So step number 2, estimate SI. What is SI? Signal power at the channel output. Signal power at the channel output. This also can be termed as signal power at the receiver input also, right? So, okay. So, how to get that expression? SI equal to 1 over 2 pi 0 to 2 pi S square of t dt, because the input to the signal or the output of the signal is S of t. Okay. For double sideband full carrier AM, it is known that S of t, the modulated signal, is given as AC into 1 plus Ka M of t into cos omega Ct or cos 2 pi f Ct. It does not matter whether you are writing cos omega Ct or cos 2 pi f Ct. Now, if you go ahead, Si equal to 1 by 2 pi 0 to 2 pi AC cos omega Ct whole square dt plus 1 over 2 pi 0 to 2 pi Ka AC M of t cos omega Ct whole square dt. Kindly remember, we are not going to use the expression a plus b whole square and simplify it. If anyone is thinking of using a plus b whole square here, What is the standard notation? A square plus B square plus 2AB. However, when you evaluate using that also, integration of the term 2AB will be automatically 0. So we are directly using the terms, the AC cos omega CT whole square, as well as the second term KA AC M of T whole square. So what I do, take AC square common, 1 over 2 pi, 0 to 2 pi, cos square omega CT dt, first term, plus second term, again, Ka square AC square common, 1 over 2 pi, 0 to 2 pi, m square of t into cos square omega ct dt. What is cos square theta? Cos square theta equals to AC square into 1 over 2 pi, 0 to 2 pi, cos square theta, 1 plus cos 2 theta. So 1 plus cos 2 omega ct by 2 dt. The second term, Ka square AC square 1 over 2 pi 0 to 2 pi m square of t into 1 plus cos 2 omega ct by 2 dt. So the first term will be given as AC square by 2 into P, first term, plus second term Ka square AC square by 2 into P. How it comes? Because the second term is there, cos omega ct, it will become 0. And similarly, here also, second term, cos omega ct will become 0. Why? Because if you integrate a sinusoid over a time period 0 to 2 pi, will be 0. So finally, the input signal power can be represented as AC square into 1 plus Ka square P by 2. This is the input signal power SI. Now, once this is estimated, we immediately make a move to estimation of input noise power, Ni. Estimate Ni, input noise power. In our previous lecture, we have already mentioned estimation of input noise power is common to all the modulation schemes. So Ni is input noise power or the channel output noise power. Remember, both are same. Ni, either you can call it as input noise power to the receiver, or same can also be called as channel output noise power also. So it is estimated over the message bandwidth. So minus W to plus W, N naught by 2 dF. So N naught by 2 is a constant. N naught by 2 outside taken minus W to W 1 dF. Integration of 1 is F. So it will be upper limit is W, lower limit is minus W, W minus of minus W is 2W. So this cancel. This will be equals to W N naught. So we have estimated the input signal power. We have also estimated the input noise power. Now, signal to noise ratio at the channel output can be denoted as SI by Ni. So that is equals to AC square into 1 plus Ka square P by 2 W N naught. This is the input signal power in DSB FCAM. Now, the next step is to estimate the output signal power SO and output noise power NO. So for this, first of all, we have to mention what is the output of the IF section. The IF section will be consisting of a modulated signal with the frequency at FIF actually, but we use FC. That is, second term is N of T, narrow band noise component. So if we represent this mathematically here, that is given as AC into 1 plus Ka M of T cos omega Ct, the AM signal, followed by noise component NC of T cos omega Ct minus Ns of T sin omega Ct. This is the signal coming out of the IF section. If you observe carefully here, it is going to be consisting of AC into 1 plus K M of t cos omega CT corresponding to message, whereas NC of t cos omega CT minus NS of sin omega CT corresponding to narrow band noise component. W of t at the input is wide band noise. N of t at the output of the IF section is narrow band noise. Okay, now from this narrowband noise and the signal component, we have to know what are the components present at the output of the envelope detector. So in this context, we are going to correspondingly draw a phasor diagram and estimate the output of the envelope detector. So why should we draw a phasor diagram here? In amplitude modulation, amplitude is important. In frequency modulation, frequency or angle is important. So for getting the envelope that is corresponding to amplitude portion, we are going to draw the phasor diagram. So while drawing the phasor diagram, we are going to assume initially that in the given system, assuming the AC, the carrier component is larger. So among the number of terms present at the output of the IF section, there are two components presently available. One is cos omega CT, second one is sin omega CT. Which one we should take as the reference phasor? AC into 1 plus K M of t cos omega CT is taken as the reference phasor. Why? Because we have assumed that the carrier power is more than the noise power. So this will be AC into 1 plus K M of t. This will be NC of t. And subsequently, this term will be NS of t. Okay. So why you have taken here NS of t? NS of t corresponding to sin omega CT, no? So it is 90 degrees with the cos component. So if you draw this waveform here, okay. Okay, this is the resultant. The hypotenuse of the complete right angle triangle is the resultant y of t. Okay. So now what is the expression for y of t? We know hypotenuse square equals to adjacent side square plus opposite side square. So correspondingly, what you can have here, y of t equals to resultant equals to hypotenuse equals to square root of, okay, AC into 1 plus Ka M of t plus NC of t whole square, the adjacent side term, plus N S square of t. Is it clear? Because the cos term and sin term are 90 degrees against each other. So the resultant y of t is a diagonal element to both of them. So diagonal equals to root of adjacent side square plus opposite side square. However, what you have assumed? We have assumed that the carrier component is larger. Where is carrier component? The first term. So the second term will be neglected. Y of t equals to AC into 1 plus Ka M of t plus NC of t. So the resultant term will be consisting of one message component as well as the narrowband noise component. If you have observed in the demodulated signal or output of the YF section, what we are consisting of AC plus AC Ka M of t plus NC of t. This AC contains no message signal. AC is the carrier amplitude, no. It contains no message signal. Simply, it is a DC component. So, by using a DC blocking capacitor at the output, by using a DC blocking capacitor at the output, the final expression for the demodulated signal will be AC Ka M of t plus NC of t. No, so the output is consisting of two components here. One corresponding to message signal, the another corresponding noise component. So let us assume SO, output signal power, 1 over 2 pi 0 to 2 pi AC square Ka square m square of t dt. That is equals to AC square Ka square outside 1 over 2 pi 0 to 2 pi integral m square of t dt. If you see this 1 over 2 pi 0 to 2 pi m square of t dt is nothing but the average power. We know na, from the definition of average power of a signal, we know that concept. So this is equals to AC square Ka square P, which is nothing but the output signal power. Now what is left over? The leftover thing is, okay, last one, NO. What is the output noise power? Okay, if I mention these steps here, S3 or S4, okay, got it. S5, we are estimating the step number 5, output noise power. Output noise power, how can obtain? It is consisting of NO equal to 1 over 2 pi 0 to 2 pi NC square of t dt. This is the expression for average power in time domain. That is okay. But do you have any expression for NC of t? No. So what is the corresponding equivalent thing? It is nothing but the area under the power spectral density of in-phase noise component, SNC of F. Let me just mention here, what is the meaning of SNC of F? SNC of F is the PSD, power spectral density of in-phase noise component, right? Okay. So as we cannot estimate the average output noise power in time domain, we are shifting to estimating the power in frequency domain. So how it will be? Same procedure what we have seen previously. Okay. So input noise density SW of F is N0 by 2. It is wideband noise. Okay, spread over all frequencies, right? The output of the IF section will be a narrowband noise that is centered at FC, right? The output of the IF section will be narrowband noise, FC plus W. Okay, yeah, this is minus FC plus W, minus FC minus W. This is N0 by 2. Hope understood how the transformation happened. The wideband noise here, this wideband noise is passed through IF section. This is the output of the IF section. Okay, output of IF section, narrowband or IF filter. Now what do you want? You don't want SN of F, you want SNC of F, the power spectral density of the in-phase noise component, which is obtained by SN of F minus FC plus SN of F plus FC. It means shift the narrowband noise PSD right side by FC, left side by FC. Okay, so we are quite familiar with operations on signals. So if I shift the spectrum towards the right side, what is the meaning of shift right side? Add everywhere, FC everywhere. So this will be minus W to plus W, N0 by 2. What is this? SN of F minus FC. And something some over here will also get 2FC plus W, 2FC minus W. Why? You are shifting this one na, FC plus FC, 2FC. So 2FC plus W, 2FC minus W. This is SN of F minus FC. Similarly, okay, how you get SN of F plus FC? Shift left. Shift left means subtract by minus FC. Have a glance. So subtract by minus FC. So plus FC minus FC, 0. Plus FC minus FC, 0. So again this will be, we are shifting left side, no, W minus W, N0 by 2, frequency. What about this? Shift left side, na? So right. Minus 2FC minus 2fc plus w minus 2fc minus w n naught by 2. This will be removed, high frequency component. And similarly, this also removed, high frequency component. So what is left over? A spectrum between minus w to plus w having magnitude n naught by 2. So then SNC of f will be addition of these two. So n naught by 2 plus n naught by 2, how much? It is n naught. So minus w plus w n naught frequency. This is the SNC of f. Now we want to calculate area under this. So NO equals to minus w to w n naught df. This will be equals to 2w n naught, which is the output noise power. So signal to noise ratio at the output equals to SO by NO. What is the output signal power? SO, Ka square AC square P. We have already estimated. So this is equals to Ka square AC square P by 2w n naught. Now what you want? Gamma or F, figure of merit equal to output SNR. How much? Ka square AC square P by 2w n naught. What about input side? Right. 1 plus Ka square P into AC square by 2w n naught. 2w n naught, w cannot cancel. AC square cancel. So the figure of merit in DSB FC, that is double sideband suppressor carrier AM, is gamma equals to or F equals to Ka square P by 1 plus Ka square P. Okay, so before we close this discussion, let me take a case. Let M of T be single tone, AM cos omega mt, for example. Then power P will be equals to AM square by 2. So what is gamma? Ka square into AM square by 2, right? By 1 plus Ka square into AM square by 2. What this will be equivalent to? We know na, from the fundamentals of amplitude modulation, we know mu equals to Ka into AM. So if you simplify, this will be equals to mu square by 2 plus mu square, which is always less than 1, because the maximum value of mu LOD is 1. Thus figure of merit. Thus figure of merit for AM with envelope detection is always less than 1. Okay, that is why, if you remember, that is why in our earlier discussions, we mentioned that AM performs much lesser or poorer than the FM signal. Okay, so this is the manner we are going to estimate the figure of merit for double sideband full carrier AM, that is going to use envelope detection. In the next lecture, we are going to see what is the figure of merit for SSBSC, that is single sideband suppressor carrier AM receivers. Okay, thank you all.